Thank you, Mega, for such good introduction. So, hello everyone. Very good morning to all of you. And we'll today's my talk is about cracking a web-based metaverse experience with WebRTC, featuring 100 ms. Just a heads up, not a sponsored talk. Just a shout out to something I liked about 100 ms. So yeah, we'll start. Okay. So cracking a web-based metaverse experience with WebRTC. So before that, a little bit about myself. So I'm a software engineer previously at Invac, and I work primarily with JavaScript and TypeScript. And this is my tech knowledge. So while at Invac, I was given the chance to work on the metaverse, which I was lucky enough to crack. And yeah, I was responsible for creating the real-time multiplayer and the challenges which we faced around that. We'll look into that. So enough about me. Let's get started. So what will this talk will be covering? So we'll be not going too deep into hands-on implementation of WebRTC server and the client side. We'll look onto the concepts which are responsible for making WebRTC possible and the protocols behind WebRTC as well as the browser APIs. Then we'll look into like should you write your own implementation of WebRTC or not. Then we'll touch upon the basics which you need to know for creating your web-based metaverse experience and relaying how to relay data using WebRTC for a real-time multiplayer effect and the performance issues which come with it and what is interpolation and how will we achieve it and optimizing the client to reduce re-renders. Cool. So let's get started. So what is WebRTC? So WebRTC, for those of you who are not aware, stands for Web Real-Time Communication. It is responsible for creating the audio-video based apps which run peer-to-peer and make real-time communication possible without requiring any extra plugins or intermediary software. It is an open source project backed by the big giants Apple, Google, Microsoft, Mozilla. And if you want to know real life examples, so the Google Meet, Discord, these are pretty good examples of WebRTC. And if you attended Amir's talk yesterday, which was amazing on real-time collaboration, you connect WebRTC and CRDT together, and you have something like Google Docs in place, which is amazing in the remote world right now, right? So protocols behind WebRTC which make WebRTC possible. So these are the network side of things which are pretty important to know before deep diving into WebRTC. So there are these five protocols which I'd say there is NAT, there is Turn, there is ICE, and there is SDP. So what is NAT? So NAT stands for Network Address Translation, right? So why do we need NAT? So before IPv6 came into picture, so there was this problem of limited IP addresses. So we would run out of IP addresses very soon. So NAT came into picture for that, and the second reason was firewalls. So you cannot expose your public IP address to the real world so easily. So NAT lets you get that protection layer as well. So how does NAT work? So suppose this is your client, this is your IP address, and you want to interact with the APIs or any. See, this is your server address, which is another computer basically. So what you can do is you put a GET request key. I want a GET request at this IP address and this port number, right? So it goes to your router. So router says, "Let me take care of it. I won't expose your IP address." So what router does is, okay, I will send this request on your behalf. There is a NAT table created inside the router, and it stores your IP address as well as port number and sends it to the destination IP address and port number. And while it goes there, when the request reaches there, it's the IP address of the router which is exposed, which is 5.5.5.5, and the port number, not yours. So it gets there and it comes back. So when the request comes back, uh, it looks up into the NAT table. Okay, the request has come back. Now where should I send it back? So it says, okay, this was coming from 10.0.0.2. So let me send it back. So this is basically how NAT works. So yeah, there are four types of NAT in picture in the current world. There is one-to-one NAT, there is address restricted NAT, there is port restricted NAT, and there is symmetric NAT. So what is one-to-one NAT? So one-to-one NAT does not have any restriction. Any request which was done via the router and the response came back, it lets it go pass through and go to the private IP without any checks. So all the request just goes through similarly. So for restrictions, there is address restricted net. So what happens in address restricted net is, so the request responses which are coming from the request, it checks in the existing net table if this address exists in the net table or not. So if so basically if I have interacted with this address before, so then I will let it go through to the private facing IP. Otherwise, I'll stop it right here and let it go through. So that's address restricted net. And other is port restricted net. So port restricted net adds one more level of security. So it checks if this response which is coming from this server, so it checks if I have interacted with this IP address as well as the port combination before. So it checks key if there is a 4.4.4 port number 80. Okay, I have interacted with this before, let it pass. 3.3.3 8080, I have interacted with this before, let it pass. And the same address but not the same port number, if I have not interacted with it, I'll not let it pass. So this is port restricted net. Now the most secure comes the symmetric net. So what symmetric net does is, symmetric net check the full pair key. Okay, so this was the destination, this should be the destination and this port number which I have interacted with before, but also this should be my the source which was there, it should be my IP address and this port number only. So it checks full pair and then only it lets it pass through. So that is symmetric net. It's the most secure one among all the nets. So how to overcome this problem of net if we want to do a peer-to-peer based network? So there are two concepts which lets us uh, bypass this net problems. So there is, first one is stern. Stern stands for session traversal utilities for net. So what it does is, stern is a separate kind of server where you send a request and you get their public facing IP address as a response. It works in the case of full cone, full cone address and port restricted net, and fails in the case of symmetric net. So how does stern work? So see, there is this stern server. You send a normal request to a stern server. The router or your internet service provider, just as normal net do, it just attaches its public IP address and passes to the Stern server. What Stern server does is, it gets your public facing IP address from the network packet and wraps it in the response and sends it back to the router and then to you. So now in the response, you know, okay, this is my public IP address, and then you can establish a peer-to-peer connection. So this is how it's done. So behind a full cone net, say, or an address or port restricted net, you send your request to Stern, get your public IP. This also does, and now both of them can interact. Okay, hey, I am this, do you want to connect? Sure. So this is the shortest way of connect peer to peer. And then there is turn. When does it fail? So in the case of symmetric net, it will fail because symmetric net says, I don't know you, I haven't interacted with you before. So symmetric net is the like the good child, it doesn't talk to strangers. So for to overcome the symmetric net, we have a turn which is traversal using relays around net. So it is also a server which relays packets to the client, and all the clients which are behind the symmetric net uh, interact via the turn server only, and it is an expensive server to maintain and run, which needs to be pointed out. And yeah, how does turn work? So turn says okay, send hello to this IP address. Okay, it sends okay, and then it says okay, I said hi, so the response comes back via the turn, and both of them are sitting behind a symmetric net and following their protocols as well. So this was to overcome the net based problems. The other protocol which you need to know about is an ICE. So what is ICE? ICE is a protocol established by the Internet Security Organizations, which is Interactive Connectivity Establishment. It basically collects all your public IP address or private IP address and the turn server addresses and the turn server addresses, and wraps it, and this all wrapped together are known as ICE candidates. These ICE candidates are sent to the remote peer via an SDP. So, what is SDP? So, SDP is Session Description Protocol. It's not a protocol, basically a format which wraps around the media codecs, your port numbers, network options, as well as the security option and the ICE candidates, which we look right now. It wraps all of them and creates a format which is basically a session description protocol. And this SDP is generated by the user and sent to the remote peers somehow. This somehow we'll look into. So how do you send it? So you need a signaling server. So HDP signaling is important because the remote peers need to know that this is the HDP generated by the user, as well as you need to know that this was the HDP generated by the remote peers, right? So you need once the HDP is generated, this needs to be transmitted to all the peers. Once it is transmitted, then the peer-to-peer is established. Before that, you need a signaling server. It can be your HTTP request-based server or Firebase or WebSockets. It's up to you, right? So this was all the concepts which are required to create your own WebRTC server sites, right? So these are some Stern servers. Some are free provided by Google. And if you need to spin up your own Stern and Turn servers, this is the open source GitHub project Coturn. You can look into that. And for the client side, there are browser API which we have. First is the RTC peer connection. So you initialize the object via the RTC peer connection constructor, and on that you uh, call this method create offer, which creates your HDP. You set it in your local description. So this is my local HDP. Then send it to the signaling server, say Firebase. Firebase stores it in and sends to the remote peer, and the remote peer receives the HDP, sets in its remote description, and then create an answer, sends it to the first user. First user sets the HDP its remote description, and then they exchange ICE candidates, and ICE candidates have the information about stern and turn. And yeah, after that the peer-to-peer connection is established. Apart from that, there is this RTC ICE candidate, which gives you information about your ICE candidates, session description, and data channel to establish the flow of the data between the peer-to-peer. To access the webcam and the microphone, you can use the good old media stream dot get user media APIs. We'll not do hands-on coding. I'll give you the link to the very good blog where you can read more about it. So next question is, should you write your own implementation? So if you want to, you can. There's nobody stopping you. But some consideration, some factors which you should consider is, you need to be ready to deal with all the challenges that come with maintaining the servers. Servers, yes, plural, because you need to maintain the signaling server, your stern server, and for the edge cases, you need to maintain a turn server as well. And if you are writing your own implementation, there is, apart from that, there is media servers also involved, which we haven't touched upon. So this all you need to maintain. Then there is the scaling issues which come with it, and the cost, time, and the dev power, as well as the DevOps power which will be needed. So if you can check all of these boxes true, you can go ahead. But uh, at Invact, we didn't. We were in a very fast-paced environment, and these all boxes were a big no for us. So this was not ideal, and you need to do this in a not so ideal world. In an ideal world, there exists 100 ms. So 100 ms was the hero. So all your stern, turn, audio, video, scaling, signaling, all the issues can submit in front of 100 ms. That's me as well. So yeah, 100 ms to take care of all your worries of related to WebRTC and peer-to-peer. You don't just you hand over 100 ms to your front-end developers, and you will have a WebRTC app in place within minutes. And 100 ms claims it, and that is true. So my love for 100 ms, it started in February when I came in contact with 100 ms team, as well as their docs. The developer experience, the SDK is so good ki you will fall in love with it. So give it a try if you are into WebRTC and going for some WebRTC application. And so now touching upon the metaverse. So if you need to know about the basics of web-based metaverse, there was this awesome talk yesterday by Shiram Balaji. You should, you cannot miss that if you are going for 3D on web. I will not go deep into the basics, and we'll just know what is minimum required for creating a minimum web-based metaverse. So you need to know good old JavaScript and some basics of 3D and coordinate geometry. So yeah, if you want to go with the vanilla JavaScript, there is this library called 3JS, which is maintained by Mr. Dube and the community. It is you will write the code in imperative way. There is class-based constructors and all. And if you like declarative way of writing and React, basically all of us here love React. So you can go with React 3 Fiber. These are the docs there. This is maintained by an awesome group, Poimandres, which Shiram mentioned yesterday. So this is the group which gave us the stand and React Spring and another awesome libraries. So you can look into that as well. So if you missed the talk, some basics which I hope you should know is, and we'll look into that, is in 3D world, everything is basically a mesh. And what is mesh? Mesh constitutes of two major things, which is one is geometry and another is material. So geometry, think of geometry is like a skeleton, and you wrap the material around it, and you have a mesh. And these meshes are the building blocks of 3D world. Apart from that, you need to know, okay, there are three axes involved in 3D. One is your X for left and right, Y for up and down, and Z for front and back. This is the all you need to know, and we'll deep dive into the code. So how will we use the WebRTC to power the metaverse? So for real-time multiplayer, so take an example of Google Maps. For a 2D map, we have two coordinates, X and Y, latitude, longitude, right? So your real-time location, you can plot based on these two coordinates. So for a 3D map, we'll need three coordinates, which we looked into, right? So you need X, Y, and Z. So let's say a local player, which is your machine, you press W and your player moves forward. So now the coordinates have changed. So we send this coordinate to all the remote players which are connected via WebRTC. Say two more players, players B and C. This is received by all the remote players, and in their map, player A is re-rendered and its position changes. So Cubeverse. So Cubeverse is the and some basic metaverse which I have created using 3D. We'll look into the code. So you can see we have HMS imported here, and so a keyboard component which I created. So keyboard component basically uh, does the take care of the WASD. So for all the four keys or the arrow keys, and it just updates the position based on the player slice, which and we have used the stand here for the state update. As soon as you press WAS or D, your state changes and the key event is registered and you move accordingly. And apart from that, everything happens in 3D inside a canvas, and you wrap everything in HMS context. And you have a sky which is provided by Dre. There is lighting, there is orbit controls. This is our player cube player, and we have remote players basically. So what happens inside your local player is just a second, I'm on the wrong branch. Cool. So what happens inside the remote player is you as soon as the key is pressed, you there is use frame. Use frame basically runs every frame, which is around 60 fps on average on an average client machine. So on every frame, if it checks if the forward, backward, left or right is true, we use HMS action dot change metadata. Metadata is basically the string which gets related to every peer and it's attached to every user ID. So we stringify the JSON object, and yeah, we just pass the information around it, so which is received by the remote players. So there is this peers data which comes from the HMS store. It's a Zustand store under the hood. So you check for if the player is not local, you filter out the local players and you map through them and you render them. So as soon as you get new positions, it just basically re-renders as we looked into the slide. So we'll look into the practical now. So yeah, we this is the welcome screen. We enter the name, we select a color, and we enter. Well, basically the cube verse is everyone is here is a cube. So yeah. So here we have XYZ. You can see as soon as the player is moving here, let me zoom out. Yeah, as soon as the player is moving here, we have a real-time multiplayer in picture now. So yep, player needs to move so for the color to relay for now. So this was basically bare minimum metaverse which I have created for this example. I'll send the GitHub repo link as well. So this is working, right? So what is happening, which that we looked into. Now looking at the performance issues which comes. So inside the use frame, I have put checks so that idle data does not go forward. So even if we update the console log here, and if you look, so now just take a look at the consoles and the number of times. So whenever the console is printing, update is going to the server, and at the same time, it's received by the window on the right, and it's re-rendering there. So this is too much, right? So take that into consideration. Let me open one more window, and this one will say www, and the yellow block it just moved. So yeah, wait. We go to remote players, we comment this out and go to remote players, and what we'll do is we get the name as well, and we say how many times the remote player is being re-rendered. So let me clear the console and let me move. So there is now there are three players. One is yellow, pink, one is blue. So we will just move the blue one and just take a look at the console in the right one. Let me click on those and see at the amount of re-renders which is happening. Just one player is moving on the left and the amount of re-renders which is happening, right? So this was the amount of re-renders. So now one thing which we need to look into is why is say if ABC is moving, so why is another the triple W which is re-rendering? ABC only should re-render, right? So both of these performance issues which we'll look into and solve. So what is the performance issues which come with the so use frame runs every frame. So the average frame rate is 60 FPS. So the position update is done inside the use frame for smooth position relay. Why we did it inside use frame? So imagine a flip book. So if you flip it from the end to the first, so you see a object which you have drawn. It should be very much near to each other so that you can see it moving gradually and smoothly, right? If you at the last page your object is here, and on the next page you leave some space and draw it here, so you will have a sudden jittery movement. For a smooth movement, it needs to be gradually increasing. So that's why we used the use frame. So it sends the position like 1.1, 1.2, and it gradually moves smoothly, which we seen. So, but the problem with this is if a player is moving for 10 seconds, there will be 600 updates going through the server to all the players. So this causes serious performance issues on both the ends, server as well as the client side, right? So this was me. We and this is 100 ms servers. After writing this code, I almost tried to burn them down. But 100 ms team was very nice about it. We sat and we came up with solutions. And the solution was we tried interpolation. So interpolation, it works by taking two old positions and moving the character between them. How does this work? So we instead of sending at a constant interval inside the use frame, we send it at a gap of some interval and basically throttling the update function. And now since the remote player used to re-render based on the continuous position, the problem which arises is it can teleport just like the flipbook which we talked about. It can teleport from one point to another, and there will be a jittery movement and teleporting issue. So to avoid this, what we'll do on the remote player side is we'll lure the player based on the two positions. So what is lure? So LER basically stands for linear interpolation. So, what is linear interpolation? It is provided out of the box via 3JS, but we'll break it down into the front end terms which we know. So we take the current position of player as one point and the new receive position as another point and LER between these two. So think of it like CSS keyframe animation. So what we do we define a keyframe animation, and you give at left initially at 0% left should be 10%, and at 100% left should be 50%, and you give some time limit and a timing function, say ease in or a cubic base here, and you when you run the animation it just goes it smoothly, right? So you just give it two positions, and it the remaining position which was skipped, it just animated out of it. So that's basically what interpolation is. Now we'll look into interpolation via code example. Let me just okay, cool. We'll shift the branch to interpolation. Cool. So here, so what we've done is we set a set interval at an interval of 200 millisecond, and every time at a interval instead of 60 times in a second, now it's going at 5 time in a second. So basically 1000 millisecond is your 1 second. So divide it by 200 and you have reduced it to 112. And when you reduce it to 112, it is a serious performance improvement on both the server side and the client side, right? So yeah, this was basically done. And on the remote player, what we did was we checked the position. If current position is not to the previous position, and basically we set the interpolating position, and this was the function which I stopped talking about. Lurk, you pass in a lurk factor and the interpolating position, and we'll look the example right now. Okay, everything good. So Again, let me just say this is ABC, red color, enter, okay, this is XYZ, blue color, enter, cool. So again 100 ms has done its magic, and we have now you can see there will be slight lag which is basically unnoticeable if you say 200 millisecond lag, but it's smoothly animating, and we have reduced performance by 112, not reduced, improved performance by 112, my apologies. So yeah, we have reduced the server calls and the re-renders here. So this was basically what interpolation did. And the second performance issue which was there, ki even if blue cube was moving, the yellow one was also getting re-rendered, right? So to overcome that, what we will do is we'll use React memo. So the why we so dealing with any web RTC, what you need to take into account is if any action is happening, you cannot write a diffing algorithm between peer to peer key. Say only this one has moved and we'll send that update. Same problem was there. So if you peers data is highly reactive coming out from the Just store, any component subscribed to it will highly re-render like a ticking bomb. So what we did was we wrapped the remote players inside React memo. What React memo does is you can look into the docs as well. If the previous props and the new props are basically the same, it will not re-render and take the last rendered result and work with it, right? So React memo checks for uh, props, and then we can optimize the re-renders based on that. So just a second, we'll shift to the re-render optimize branch, and yeah, you can see here we have wrapped it inside a react.memo. I'll remove the console log comment again, and we'll see. Okay, there is some error. Keywords. Yeah, today the main restricted folders. Okay, wait. Name is string. This was working. Good. So I'll just pass it through this TypeScript. Some we'll look into that later. So we again do ABC, blue color, and enter. We need to re-render this to change the color. We have then XYZ of red color and enter. We just change the angle, and we'll have now another tab open. Into TypeScript. We'll have www here of pink color. Cool. So now we have three cubes in position. So, but what you can let me clear the console here, and let me clear the console here as well. So if now one place moving, not you can see the infinite re-renders which was happening earlier, and now we have optimized the client side re-renders to just the player which is moving, only that will re-render, and if red and pink are not moving, that re-render is not happening. So we again optimize the client side as well, and basically 3D takes a heavy toll on your client side for the performance, and you need to optimize as much as possible for a smooth immersive experience. So that was all from my side. That's all. And credits. So I learned about WebRTC in depth from this Hussein Nasser YouTube channel. Amazing crash course you should see. If you want to have a basic implementation of your WebRTC, you can hit up Fireship, and you will have a good. There is a good blog also attached with the video, and you can implement your WebRTC. Then there is MDN Docs. Apart from that, credit goes to good friend and senior Shiram Balaji, who's helped me a lot during the entire process. Team at 100 ms and my team at Invact, which were both of them were good support system, and the images and memes which they have used, and if they are now converted to an NFT, credit goes to them, the respective owner as well. So yeah, let's have a chat if you want to know more about 3D on the web or web RTCs in general. Collaborative work on web using WebRTC and CRDT. If you want to know, hit me up. I'm making a side project based, and anything about software engineering in general, I'm happy to chat about. And yeah, these are my GitHub and LinkedIn username as well as Twitter username. You can connect with me there. And thank you everyone for coming to my talk.